Okay. So this is super directive beamformer. Now we understand. Okay? So it's very nice. And then we can move on to robust super directive. Actually, we can talk about robust anything. Robust maximum directivity factor, robust. Robust, it means that when we estimate some information, that it will be robust to error in that information. Okay? So robust super directive, it can be robust relative to a few things. When you talk about robustness, it means robustness regarding some errors. So the errors in this, what I'm going to talk, is error in the environment. So super directive beamformer, it means that we designed the beamformer that it will maximize the array gain for diffuse noise. But then, because of error, because of non-ideal sensors, we also have thermal noise. So because of the thermal noise, we will get amplification of the thermal noise at the output of the beamformer. So this is sensitivity to error. Okay? So we can talk about different types of error. And then when we try that something that we design in an optimal way, we define an optimization problem, and we make assumptions. Everything is accurate. And then we check the sensitivity of what we design, the optimal design. We check how it's sensitive to some errors in our assumptions. And we see that for some assumptions, it's very sensitive. Just like we showed that the maximum directivity factor beamformer, I'll show it here. Okay, the maximum directivity factor beamformer. So this is the white noise gain that we obtained with the maximum directivity beamformer. So we see that for this example, the white noise gain is very, very low. It means that we designed the beamformer to maximize the array gain in diffuse noise environment, but then because of thermal noise, it will not perform well. So if the environment actually, it doesn't contain, we have no thermal noise, maybe the sensors are ideal with no thermal noise, then we are good, no problem. Then we don't need to talk. You know, when you make assumptions and the assumptions all are good and correct, no errors, no need to talk about robust optimization. Robust optimization, it means that we make assumptions, but then the assumptions are not fully correct. So thermal noise here, we assumed when we design maximum directivity factor beamformer, we assume only diffuse noise. But then in practical environment, we also have thermal noise. And then we see that because the white noise gain is so low, it can come to minus tens of dB. Very, very low. It means that in practical environment, we will get amplification of the thermal noise at the output of the beamformer, which means that the maximum directivity beamformer is not robust to thermal noise because it cannot handle error such errors of thermal noise. So how do we deal with that? So we need to change the optimization problem such that it will perform, it will have some constraint or perform better when we have also white noise. So the solution to something like that is very easy, okay? How do we, so this is an approach that you can use for anything that you do in your research, anything that involves optimization. So instead of using this problem, you see, this optimization problem is to obtain the maximum directivity factor. So instead of this problem, I will add another constraint. Okay, I will add another constraint. So the white noise gain, let's call it the white noise gain, that is obtained using H, the filter, the beamformer. I want it to be larger, so I can add a log or something like that, okay, if you like. But I would like that it will be larger than a certain value, a certain threshold. So if I add this constraint or this requirement, it means that we know that this beamformer will achieve maximum directivity factor under these two constraints. So a signal that comes from theta d will not be distorted, and the white noise gain for the frequency f, for any frequency f, will be at least as large as W minimum. Very simple. So we change the optimization problem. But when we add constraint, so eventually we will reduce, we will get lower array gain. Because something, when we add constraint, the performance or this minimization will be less. So the directivity factor will be somewhat reduced. But it's okay, because we are willing, it's a trade-off. If we want to increase the white noise gain, we want to increase, especially in the low frequency, it means that the directivity factor in this frequency will be lower, because we added an additional constraint. This is the way to deal with robust optimization problems. So you can do that with any problem, okay? So how do we solve this? How do we solve this problem? Very easy, okay? So instead, let's call to the directivity, okay? So instead of maximizing the directivity is like minimizing 1 over the directivity, okay? I will write it like this. So we want to find H such that the directivity factor is minimized, okay? But instead of subject to this constraint, of course. Okay, I will write it. But instead of minimizing this, I can minimize this plus epsilon 1 over white noise gain. Something like this. And then I can write these expressions, the array gain for diffuse noise and the array gain for white noise gain more specifically. Okay, so if what I did, when I have additional constraint, I can give them certain weight. Okay, subject to H df cosine theta d equals to 1. Okay? Now, if epsilon is 0, what does it mean? Not robust, what we did before. So it will maximize the directivity factor. If epsilon is larger than 0, if I increase it, the more that I increase this, I give more weight to this requirement. So when I increase epsilon, so I give more weight, so it will try more to minimize this. So it will maximize, it will increase the white noise gain. But then it will increase the white noise gain and will decrease the directivity factor. So epsilon is like a trade-off parameter to control between white noise gain and directivity factor. By the way, whenever you have trade-off between two things, you can add parameter. If I have 3 things, I can add another parameter. Okay? And the parameters control the weight, how much weight. Now, if I want to satisfy this constraint, I can choose epsilon for each frequency. I can put here epsilon as a function of frequency. And for each frequency, I can change this. I can change such that there will be equality here. So I increase the white noise gain until it reaches W minimum. So this parameter will depend on the frequency. Okay? Very easy. So let's see here. Let's see how we do it. Now that you understand, it's very simple. So suppose that I take the super directed beamformer, okay? And instead, I can write the directivity factor specifically. This is the array gain for diffuse noise. The array gain for diffuse noise is the directivity factor that is obtained using the beamformer H. I can write also the expression for the white noise gain. This is the array gain when the noise is white, spatially white. So I have here a matrix, which is identity matrix. So this is the expression for the white noise gain. And then I will try to minimize this. 1 divided by D plus epsilon, 1 divided by W, the white noise gain. So if I increase the Lagrange, this is a Lagrange multiplier. If I increase it, I give more weight to this part. So I will increase the white noise gain, but I will get lower directivity factor. Okay? So I can write it like this. So it's beautiful that I can find this expression. You see, this expression, when I add epsilon, it looks like this. You see? So this is a very nice expression. Why? Oh, there is a mistake here, -1, okay? Just a minute. Oh, no, it's okay, it's okay. Something like that. So it's a very nice expression. Why? Because the solution to minimize this under the distortionless constraint to the direction theta d, this is the solution. You see, so what we did here, instead of minimizing the directivity or maximizing the directivity factor, or minimizing 1 over the directivity factor, and then here we have a matrix, this matrix. Now we replace this matrix by this matrix. So this is the solution. Straightforward. You see, just like the maximum directivity factor, but instead of gamma 0 pi, which is the correlation matrix that corresponds diffuse noise, we have this matrix plus epsilon I, identity matrix of size m by n. So the solution, this is the solution. So this solution is more robust You see, it's very nice to see that it's robust because, as you know, when you invert a matrix which is singular, we know that the solution is not robust because when you have a matrix but which is close to be singular, maybe it's invertible, but it's close to be non-singular. How do we know if a matrix is close to be singular or not? Condition number. Yeah. What is the condition number of a matrix? Yeah. So all the eigenvalues of the matrix, it's a symmetric matrix, right? So all the eigenvalues are positive. So for symmetric matrix, all the eigenvalues are positive. We take the ratio between the maximum eigenvalue divided by the minimum eigenvalue. This ratio is the condition number of the symmetric matrix. If it's large, it means that the smallest eigenvalue is small compared to the maximum. So if this ratio is large, it means that the matrix is close to be non-invertible or singular. So when this ratio is large, we get non-robust solution, which means that the solution is sensitive to errors. Here we see that it's sensitive to thermal noise. But it makes sense. It makes sense. The sensitivity to thermal noise comes from this inversion of a matrix which a high conditional number. So what did we do here? We added epsilon multiplied with identity matrix. What happens to this ratio? So instead of this ratio, we have eigenvalues. You know, if you take symmetric matrix, you add epsilon I, the eigenvalues actually become plus epsilon. So this will be the maximum eigenvalue of the matrix gamma plus epsilon I, and this will be the minimum eigenvalue. So you see, epsilon plus max, it doesn't really matter, because if you add the small epsilon to the maximum eigenvalue, it's not going to affect it. But the denominator is going to be really affected. So you see, when epsilon is larger, this ratio becomes lower. So we decrease the condition number when we increase epsilon. So this is a really well-known method to make symmetric matrix more regular. That's why, so when you have this matrix is symmetric. Yes, all the eigenvalues are positive. If you have symmetric matrix, okay, so you have the maximum eigenvalue and the minimum eigenvalue, they are finite. And then if lambda mean is 0, it means the matrix is singular. So of course you cannot invert a singular matrix. But even if it's not 0, suppose that it's full rank, but this ratio is high, so it comes closer to be singular. So if you want to decrease this ratio, you can add epsilon to the diagonal, which means you add epsilon to the eigenvalues, and then you decrease this ratio. So by decreasing this value, this ratio, this condition number, it means that you make this matrix more regular. That's why epsilon is called regularization parameter because it makes the close to singular matrix, it makes it more regular, this parameter. Okay? So this is a well-known method to regularize symmetric matrix. Okay? And we see it very beautifully that we obtained it from the way we use the trade-off between directivity factor and white noise gain. Let's see an example. By the way, instead of epsilon like this, instead of a parameter like this, sometimes we can, we can do something instead of epsilon. So this is the super directive, of course, with epsilon that depends on f. We can do some regularization like this. So instead of gamma 0 pi plus epsilon I, we can take 1 minus alpha this plus alpha this, which is similar, but it enables us to use alpha between 0 and 1. Because here, epsilon is between 0 and infinite. So here we can use alpha between 0 and 1. And the relation between epsilon and alpha is like this. So it's just another way to do regularization or trade-off between two values that we want to optimize. And we obtain the white noise gain and the directivity factor using this regularization. So if we go to the example that we showed before with the maximum directivity factor, and we take regularization coefficient alpha, so you see here in this example the white noise gain that is achieved, the white noise gain as a function of frequency for different values, different number of sensors. So the blue one is with 2 sensors, then 4 sensors, the green, the red is with 6 sensors, and the light blue is with 8 sensors. So different values. So this is the white noise gain, and for different values of alpha. So alpha is between 0 and 1. So if it's very small, if it was 0, it means that we don't give any weight. Okay, so because 0, it means we don't give any weight to the white noise gain. So the white noise gain will go to minus, we saw, minus 100 dB, minus 80 dB, very low. But so here, in this example, alpha is 0.001. So you see, alpha is not 0, it's larger than 0. So it didn't go down too much, the white noise gain. If we increase alpha, so it means we give more weight to the white noise gain, so it increases. And if alpha is equals to 1, it means that we only optimize the white noise gain. Directivity factor, we don't care. So when alpha equals to 1, we obtain the beamformer that maximizes the white noise gain, which is the delay in sum. Okay? So this is the delay in sum in this case, alpha equals to 1. So you see, we know that the white noise gain is maximal. See, it's maximal. So of course, as we increase alpha, the white noise gain increases. So if you compare the blue line here compared to the blue line here, it's larger. And here it's larger, and here it's larger, for any frequency. And we can also plot the white noise gain as a function of alpha for different numbers of sensors. So you see here, number of sensors, 2, 4, 6, 8. So for a given number of sensors, as we increase alpha, this is for 1 kilohertz, 2 kilohertz, 4 kilohertz, 8 kilohertz. So for a certain frequency, let's suppose that we work with 4 kilohertz. As we increase alpha, we give more weight to the white noise gain. So you see the white noise gain increases. And for any number of sensors, it increases as we increase alpha. What happens to the directivity factor when we increase alpha? What do you think? What happens to the directivity factor? When we increase alpha, the white noise gain increases. So what happens to the directivity factor? Decreases. We pay for that. This is the trade-off. So you see that here the directivity factor as a function of alpha decreases. The maximum directivity factor is obtained for alpha equals to 0. But then the white noise gain will be very, very low. So we increase alpha, we increase the white noise gain, but the directivity factor decreases. So suppose, let's go back for just a minute. If I go back to the white noise gain, okay? So this is the white noise gain as a function of alpha. And this is for 4 kilohertz, for example. So I can choose alpha. You see if it's low, it's here. Suppose that I want to choose alpha such that the white noise gain will be larger than 0 dB. 0 dB here. So I will choose this alpha. What is here? This value. I will choose it for 4 kilohertz. If I want it to be also larger than 0 dB for 1 kilohertz. So alpha for 1 kilohertz will be this value. So for each frequency, I can choose alpha for each frequency, different alpha, such that the white noise gain will be larger than 0 dB. Or a different threshold. But suppose that the threshold is 0 dB. Okay? So alpha depends on the frequency, the optimal alpha. And then, if I go to the directivity factor, you see that the directivity factor for this alpha, it will be lower than the maximum that I can achieve because it goes down using this value. So I can compute the directivity factor for that alpha and for that frequency. It will be lower than the maximum directivity factor that can be achieved. Because there is a trade-off between white noise gain and directivity factor. Okay? Any questions? We call this method robust beamforming. So if we use robust beamforming for super directive beamformer, so it's robust super directive. If we use it other methods, so it can be robust based on what are the errors. Okay? It's very nice to mention also, this is something which is nice, because I talk here about thermal noise. Many times when you manufacture, when you design a beamformer, you assume that the sensor are in certain positions. But in practice, because of inaccuracies in the manufacturing process, sometimes the sensors are not exactly in the place where you designed it. Suppose that you have smart glasses and the microphones are not exactly where you designed. There are some errors. So this kind of error. So you want that your design will be robust to these errors. And there are other errors, important errors. Sometimes you think all the sensors are the same. So the sensors have sensitivity, which means magnitude sensitivity and phase sensitivity, which are the same. All the sensors are ideal. But when we manufacture sensors, microphones, antennas, underwater communication, any sensor, They are not ideal. They are not the same. So we have some differences between the sensors. And then we can ask ourselves, how is the performance sensitive to differences between the ideal sensors and actual sensitivity of the sensors and the differences it will affect? So when you look at the design or at the specification sheet of a sensor, you need to verify what is the error of the manufacturer regarding the magnitude response, phase response, frequency response, and so on. These are important specifications because it tells you what can be the errors or the differences between sensors. And then you can design your filters or your beamformer or whatever device in actual design that will be robust to these errors in practice. Okay? And this is important. This is robust design. Because if you just take the mathematical model, you assume everything is correct, you go to a real design, a real device, it doesn't work. And you don't understand why it doesn't work. Because you didn't verify what are the assumptions and what are the errors in the actual device. So you need to take these specifications into account when you design a device in practice. This is very important. Here we see the beam patterns that are achieved by the robust super-directive beamformer. So you see here, we see this is for 1 kilohertz, 2 kilohertz, 3 kilohertz, 8 kilohertz. When alpha is small, it means that we give less weight. It's small, it's larger than 0, but it's less weight to the white noise gain. We give more weight to the directivity factor. So we get these beam patterns. You see why all the main beam are directed to 0 degrees? Why? Because here the beamformer, what kind of beamformer? Super directive. And super directive that is designed with uniform linear array, we can prove that the max super directivity is obtained for theta d equals to 0. Very nice. It shows that you listen to what I say. You understand. Very good. Very good. It's important. So the main beam is directed to 0 degree. Very good. Now, we see that when the frequency increases from here to here, from here to here, so on. So this is higher, 8 kilohertz compared to 1 kilohertz. You see the main beam becomes more narrow. Okay? Because we didn't put any constraint on the width of the main beam. So generally, if we don't put any constraint, it tries to maximize with the minimal constraints. So the minimal constraint is that the main beam is directed to 0 degrees. We didn't put any constraint on the width. If we had constraint, the performance will degrade in other, regarding other measure. Okay? But here we didn't put, so generally it becomes more narrow when we increase the frequency. Now, if we increase alpha, what will happen? What will happen to the beam pattern? If we increase, okay, let's think for a moment, okay, gradually, okay. So when we increase alpha, we give more weight to the white noise gain. What will happen to the directivity? Will come down, will decrease, okay. If the directivity factor decreases, what does it mean on the width of the main beam? If it decreases, the directivity factor decreases, so it becomes wider. Because if we have a wide main beam, So what is the directivity factor? It's actually the ratio between the value with this direction. With this direction is always 1, 0 dB. Okay, so it's always 1. And we divide by the integral over all directions. So if the main beam becomes wide, it means that we have lower directivity. Okay, so for each frequency, when we increase alpha, let's increase alpha, and we will see that the main beam becomes wider. Now you understand what is the relation between alpha and the width of the main beam. Oh, sorry, here. You see here now alpha is 0.1 instead of 0.01. So we increase it by a factor of 10. And if we compare the main beam, it becomes wider. If we increase alpha, just a minute, if we further increase alpha to 1, it's even more wide. See, it becomes wider. Okay, so I will jump so you can, here 0.1, 1. I will jump between these two. Okay, you see, 0.1, 1, 0.1, 1. See what happens? The main beam becomes wider when I increase alpha. It makes sense. Any questions? The next topic will be null steering with fixed beamformers. Okay, so I prepare you. I will talk about it tomorrow. But I just want you, because I want to give you some discussion. What is null steering? You see, with fixed beamformers, I assume that I know directions. So I know the direction theta d, the direction of the desired. Now suppose that I have some interferences from certain directions. So I remind you that with fixed beamformers, I assume that the noise field is either spatially white or diffused or combination of these two. Combination of these two with the parameter epsilon or parameter alpha, what we showed. So combination, it means that I try to optimize both with a trade-off. So this is a trade-off parameter. So if I have an interference from a certain direction, I will not be able to reduce it. So with null steering, I try to add more constraints, additional constraints, that for certain directions, I will have zero of the beam pattern, zero response. Why? Because I know. Suppose that either I know or I can estimate or find the direction of interference. So I can modify the fixed beamformer. Okay? So sometimes I do it offline in advance and I fix it. Sometimes I do it online. Okay? Suppose that I design a smart glasses. So I can design that the response, the maximum response will be towards this direction. And I can maybe put a null on another direction. What will be another direction? This is a nice question. Okay? Suppose that I take the smart glasses and I put the desired source, I will put it in front of me. This will be the direction. And I want to put a null on a different directions. Okay? So let's think. Smart glasses, they have microphones. They have also loudspeakers here. And I don't want to get feedback of the loudspeaker at the output of the beamformer. So I will add nulls on the loudspeakers, the signals that come. So the source will come from the direction of the loudspeakers. So I don't get feedback. Remember that sometimes when they increase the volume here, you hear like howling or very loud noise because of the feedback. This is very disturbing. So it's very disturbing for hearing aids. So if we want to add nulls to that feedback, to reduce that feedback, we add null on the beamformer. So we will talk about null steering. It's a very practical way, as long as we know the direction or we can estimate it. And if we don't know these directions accurately, theta d, we don't know accurately because we estimate it online. Or we estimate the direction of interference. We don't know them accurately. What do? We design robust beamformers that is robust to these errors. So it's called robust beamforming. When we talk about robust beamforming, you need to know it's robust regarding to what? So regarding to these directions. So you can read about robust MVDR, robust LCMV, robust beamformers. When the robust, either regarding the noise or regarding the directions, so you can modify this optimization regarding to some errors, okay? So we will continue to discuss the null steering, and then we'll continue with adaptive beamforming, which will not take us much time because it's very similar to signal enhancement. We just change, instead of steering vector that is based on the relative transfer function, it is based on the directions. Questions? Very good.